Hello everyone, it's my honor to introduce our latest work, HODOR, Reducing Attack Surface on Node.js with System Call Limitation, and Wang Wenya comes from Shanghai Jiao Tong University. First, let me introduce the other contributor. Wang Wenya, Gao Wang, and Gu Dawu come from Shanghai Jiao Tong University. Lin Xiuwei comes from the Ant Group. Wang Jinyi comes from Zhejiang University. Node.js stands as a beacon of innovation, an open-source, cross-platform JavaScript runtime environment that has revolutionized the way we build web applications. Its design, although reliant on a single-thread architecture, breaks performance barriers with its non-blocking, asynchronous, and event-driven nature. Furthermore, Node.js boasts a truly cross-platform approach, enabling JavaScript developers to seamlessly create and develop applications across diverse environments. This universality fosters a coherent development experience, regarding of the underlying operating system. The Node.js ecosystem is further enriched by its package manager npm. This tool streamlines the process of managing and acquiring packages, serving as a vital resource for developers to extend functionalities and share code. Node.js architecture is composed of 4 layers: the Node.js application, the built-in module layer, the binding module layer, and the dependency module layer. At forefront are Node.js applications, which are empowered to interact with a system kernel by using built-in modules. Take the execute method within child process built-in module as an example. This method allows Node.js application to utilize the system call execute to execute the string command. The built-in module layer written in JavaScript code and the binding module layer written in C++ code encapsulate essential functionalities, allowing developers to harness the full potential of Node.js engine. These functionalities are in turn supported by an array of dependency libraries that lay the groundwork for Node.js. Among these, the V8 engine stands out as JavaScript interpreter, translating our scripts into executable machine code. And libuv offers a pivotal contribution, managing asynchronous I/O operations and empowering the event loop. While this capability enables Node.js applications to interact with the low-level system kernel, they also introduce potential security threats. By using the arbitrary command or code execution. Consider the glue package as an example. The attacker can exploit vulnerabilities by injecting arbitrary bash code into execute method at line 15. It enables the attackers to access sensitive files, establish a socket connection, and even escalate privileges. Even worse, the research has shown that nearly 20% of packages in NPM ecosystem depend on vulnerable package, and most of the vulnerabilities may lead to gadget chain attacks, inject-related attacks, and supply chain attacks. And the dependent relations would expand a malicious package to large attack surface. So, how to reduce the attack surface of such malicious attacks for Node.js applications? In this work, we focus on the limitation of the attack surface of arbitrary code or command executions. At the source code level, existing efforts leverage program analysis to eliminate useless code, aiming to reduce the attack surface. Yet, such measures fall short in curtailing the attack surface associated with arbitrary command executions. This shortfall is due to the attacker's ability to execute bash command independently without relying on any Node.js independent package dependencies. The Seccomp mechanism appears to be effective in mitigating the arbitrary code or command executions by restricting the available system call set for a given application. Well, implementing the Seccomp mechanism in Node.js engine poses two unprecedented technical challenges. The first challenge is to conduct cross-language program analysis at source code level to generate a precise system call list. The second challenge is integrity with the Node.js framework. Since Node.js operates within a single process that creates two distinct kinds of threads, namely main threads and thread pool threads. Different thread type needs different restriction profile, and the thread pool threads are in charge of asynchronous I/O operations, and the Seccomp mechanism would lead to the filter Seccomp mechanism would lead to the filter of thread pool threads inheriting the filters of the parent or the main threads. So to prevent the unintended inheritance, we must carefully install the Seccomp mechanism. In summary, in this work, our goal is to minimize the attack surface in the system call level to prevent malicious critical operations, while not affecting the application's normal executions. So, therefore, in this work, we present HODOR, System Call Level Protection System for Node.js applications. It's a lightweight runtime protection system. There are 4 steps. At step 1, we construct call graphs for different layers, and then we build mappings for different layers based on the call graph, and then we generate the system call whitelist for the given application, and finally we install the system call list into the Node.js engine and execute the given Node.js application. Let's step into the details. At step 1, we construct call graphs for different layers. At JavaScript source code, we make the following optimizations comparing with the existing work. For JavaScript code, first we consider the code feature of built-in methods pattern. For the built-in methods that are executed and the argument passed to this method are also executed. To address these cases, we utilize static program analysis to identify this this built-in method with these code patterns and record the corresponding nodes or edges in the call graph. Secondly, as for the call edges caused by the dynamic nature of JavaScript code, we record the related nodes and edges by using the dynamic program analysis. Thirdly, for the necessary system calls required by the bash code in the Node.js applications, we record the bash code and add them to the system call whitelist. We re-implemented the Gen framework presented in ISTA and applied the formal optimization. And for dynamic analysis, we employed the node-proof tool. And additionally, we have utilized the Linux trace utility to trace the necessary system calls. For C or C++ code, we utilize context-insensitive analysis. However, in this work, we identified two code patterns that may lead to some false positives, namely switch case statement and function pointer parameter. To address these cases, we implement the partial context-sensitive analysis. For partial context-aware analysis for switch case statement, we consider the example depicted in this figure. The functions UVFS access at line 3 and UVFS write at line 7 both invoke the UVFS work function detailed at line 14. Within UVFS work, a variety of logic is executed through switch case statement, with only one case branch being reachable. A context-insensitive analysis would inherently inaccurately predict that all branches of the switch case statement could be reached, leading to high false positives. To mitigate that, we employ backtrace analysis and function copy technology. We identify functions like UVFS work and then gather context information at each call set, which enables us to discard the case branches of this function that are not reachable. And for the case of function pointer parameters, consider the scenario in this figure. Here, the read function at line 1 and the unlink function at line 4 and remove directory at line 7 invoke the call function at line 20 through varying call chains. Ultimately, a function pointer fn is executed with its value being contingent on the distinct call chains. The context-insensitive algorithm inaccurately assume all potential functions, such as UVFS read, UVFS unlink, and UVFS remove directory could be called through fn, leading to false positives. To address this, we trick all functions that invoke function pointer and conduct backward data flow analysis to pinpoint the precise assignment location of this pointer, documenting the respective call chains. Subsequently, we traverse the call chain and duplicate each involved function, ensuring that every unique value of the function pointer is passed to a distinct clone function, akin to call. At a second step, we get mappings of the different layers based on the call graphs. We build call graph traversal for call graphs of the Node application binding module layer and dependency layer, and we build LLVM paths for the built-in module layer. And at step 3, based on the mappings, we calculate the system call whitelist for the Node.js applications. Moreover, we divide the system call list into system call required by the main thread and the system calls required by the thread pool. And finally, we install the restriction profile on Node.js engine. In this work, we divide the applications into thread pool disrequired applications and thread pool required applications. For the thread pool disrequired applications, they do not require asynchronous operations and run solely on the main thread. Therefore, we only need to load the main thread filter, since the thread pool would not be loaded. And for the thread pool required applications that utilize different kinds of threads, they would submit the asynchronous tasks to the thread pool. Therefore, to prevent the thread pool threads from inheriting the main thread filter, we should carefully choose the timing of loading the filters. Therefore, we follow a two-step process. We first install the filter for the thread pool thread, and then install the filter for the main thread. And in this paper and in this work, since the read or write system call are widely used by the Node.js engine, we cannot limit the execution of read or write system call. So we use change root mechanism and switch the ownership of the sensitive files to prevent the attacker to read or write the sensitive files. Finally, we evaluate HODOR. 169 packages suffered from arbitrary code or command executions. 3 large-scale real-world applications, Node.js core tests, and 4 well-known web frameworks. And the total result shows that HODOR can reduce the attack surface of Node.js applications to nearly 20%. And for the call graph constructions and the resulting protections, the results show that the optimization of JavaScript call graph constructions helps identify hidden requirement system calls for 23% packages. The optimization of C or C++ call graph constructions further reduced the system call permission by 71%. HODOR reduced the attack surface for the mean thread to 19%, for the thread pool threads to 7%, while not affecting the application's normal operations. As for exploit mitigations, we first construct different advanced attack payloads to simulate various dangerous behaviors of attackers, where a variety of critical system calls can be invoked, and the results show that HODOR can effectively mitigate the execution of 73% exploit. And we compare HODOR with the state-of-art protection mechanism MIR presented in CCS, and the results show that HODOR can defend against a wider spectrum of attacks with less runtime overhead, and the overhead can be negligible. And in conclusion, we perform a crossing language program analysis with several optimizations, and we design a novel protection mechanism for Node.js applications, focusing on thread level and system call level security. That's all. Thank you.